Okay, well, how do we hide this? Hide video panel. Okay, so this is a paper that was in a very popular journal called Lab on Chip. It was from a group out of IBM, and they really took a lot of time to walk us through how bubbles form and what we can do about them inside of the device. So I'm just going to do, we're going to do a broad walkthrough of it and see what comes out of discussion. Okay, so the beginning of the paper really walks through the physics of how bubbles are formed in liquids. They run through a lot of math, and they have laws such as Henry's law and different, a lot of just different math. But we can really simplify all of this algebra with two main ideas. When you have a bubble inside of a liquid, if you increase heat, the bubble grows. And it's, intuitive to think about having a pot of water on a stove. If you heat it up, you're going to see bubbles that form and they increase. So increasing heat causes bubbles to grow. And then the second idea is that when you decrease pressure, your bubbles will grow. And again, we can think of this intuitively. If you put a jar of water into a vacuum chamber, you're going to degas the liquid, the bubbles will grow. So big picture, that's how it works. Now, how do we apply this to a microfluidic device? So let's keep going. So with increasing heat and decreasing pressure, that doesn't cause bubbles on its own. You need nucleation. They call them Harvey's nuclei. And basically how this happens inside of a microfluidic device, if you look at portion B of this figure, most surfaces have micro cavitations in them where air can be trapped when advancing liquid comes over it. These micro cavitations, these micro Harvey nuclei, they then grow with increasing heat or decreasing pressure. So, and then they give a lot of math, not a lot of math, but they talk about angles, advancing angles, and contact angles, which increase the likelihood of trapped air or not. And there's certain things that we can do to decrease these angles to help prevent cavitations of air. Okay. So the paper then walks us through different microfluidic chip designs. If we look over at figure part A, they talk about dead spaces. So we have a capillary, which is a tube that runs to your microfluidic device. Then there's a Teflon tube that's connected to the device that your capillary tube enters in. This is your connection. And usually your Teflon tube is something that you can tighten to make a airtight connection. And then you can put epoxy on the Teflon tubing to prevent air from entering into your device. So even with a perfect connection, we still have what are called dead spaces. So if you look to the far left, they call them air pockets. That dead space right there, when liquid enters into the device, it just skips right over that dead space and creates an air pocket. And then if you look at the small little air pockets on the upper right side of figure part A, those are also dead spaces. So if you have a device that is cold and you heat it, you infuse it with liquid, and then you put it into, say, an incubator to grow cells, increasing heat will cause those bubbles to grow. If you have a pressure drop, the pressure drop will cause those bubbles to grow. And so with regard to pressure drops, the pressure is the highest at the pump, and then as the liquid travels through your tubing, the pressure will drop due to hydraulic, what do they call that? Hydraulic, tension, yeah, hydraulic pressure. So energy is lost on the sides of the tubing as it travels down the tubing. So you have pressure drops automatically. And then also, pressure is directly correlated with velocity and fluid volume. So as your volume increases, say going into a device, you go from a skinny little capillary tube into a larger area, you're going to have a pressure drop. So again, pressure drop and heat doesn't automatically cause bubbles, they cause them to grow. So if you have trapped air in your device with these stipulations of a microfluidic device, it'll automatically cause these bubbles to grow. They suggest, in this case, if you have to have dead spaces, in figure part B, they recommend one possible way around this is to fill those dead spaces with PDMS, with a wire running through the PDMS. So they have the capillary, which is your tube going into your device. And through that tube, you have a wire. And then they fill the dead spaces in with PDMS. And then when it's time to use the device, they pull the wire out. And then what's left is a straight pathway for your fluids. And the PDMS fills in all of the dead spaces. So that's just one suggestion that you could possibly use to help fill in those dead spaces. They walk us through different microfluidic designs and how we can potentially ameliorate trapped air. So part A are micro grooves that you may need in your device. So there's a lot of right angles here that cause a large contact angle where the liquid will just flow right over those grooves. They recommend, instead of using right angles in your design, you see option 1 and part A is to just taper your sidewalls. Instead of right angle, open it up so that it's larger than 90 degrees. This will cause a smaller advancing angle, or I'm sorry, a larger advancing angle, and you'll be more likely for the liquid to fill in those grooves. Another option, if you can't taper your angles, is to add a soluble material, such as, what did they use? It was some type of sugar. I have it written down. I'm not good on the fly like this. But anyway, there are options where you can add materials that will dissolve in liquid so that the first time that you fill it, these right angles will be filled up and the angle will be larger and liquid will be more likely to enter into those spaces. And then over time, this material can dissolve. And it's some type of sugar, but we can follow up with that in the comments, the YouTube comments. So part B of this figure, they talk about corners and dead ends. So if we see the first one, we have a right angle of liquid traveling through. They recommend, because of the angle, the advancing angle on a right angle like that, air can get trapped in the corner. They recommend making a softer corner instead of a right angle, kind of just making it more of a slope. So that's not always possible. If you have to use right angles, they recommend possibly using a vent. So what we do with a vent, in this area where you have air trapped, you have an exiting vent that's hydrophobic. You have to make this vent smaller and hydrophobic for the liquid not to enter it. And that way the pressure can release out of there. The liquid will go right up to the vent and then, but not go through the vent and exit the device. So you have to make sure that your size is correct and that that you have a way to make your venting hydrophobic. And you can do that with different materials. They're not on the tip of my tongue right now, but again, we can follow up in comments if this is something that interests you. Okay, let's move on to part C. So when you bond chips, microfluidic devices together, usually you have different layers, and typically when you bond them together, there can be lots of cavity spaces in between the bonding. Even if you're using glue, it's really hard to make a perfectly smooth area. And this is a place where nucleation and air entrapment can occur. So they recommend using PDMS or some other type of malleable glue like resin to fill in these spaces. And then part D, this is for large chambers in a microfluidic device. This looks a lot kind of like our device that we work with in asteroids and humics. When you initially fill a chamber with liquid, if the liquid wall doesn't travel at the same time, the liquid advancing can cause islands of air pocket. So they recommend adding structures that will help to guide the liquid to travel at the same time, such as pillars or different guiding posts within your device. So for the sake of time, I'm going to go ahead and travel through this. We're through our 10 minutes. Really quickly, another option for filling a large chamber and preventing air pockets is to use liquids that have a lower affinity for hydrogen bonds. Water really likes to stick to itself, but if they recommend maybe putting ethanol through your device first to fill in the area with liquid, and then once your device is totally wetted and filled, you can flush it with whatever culture media or water or whatever it is you're using to do your experiment. Here they show ethanol and they show water plus 10% SDS to fill in your chamber. So that's definitely a good option. A pre-wetting with ethanol maybe. And that's all we have. So it was a very broad overview, but we're going to move on to the next section, a 15-minute discussion. So again, this is very casual, and there's no wrong answers or thoughts. But what do you guys think?
I have something like, can you go back to the next slide on the next one? I agree that the first one, like, can you go back to the yeah, so the decreasing pressure, growing rubber, we had the same issue in our device, the VFA housing. So what we did, so the VFA, the chamber, there is the height, we didn't really care about the height of the fluid inlet. So the height was, I think, 1 millimeter, 1.25 millimeter.
That's huge.
So the diameter is around 2.5 millimeter. So whenever we are passing the liquid, so we always see the air.
Yeah.
So then I have no idea because I'm not really great in that microfluidic part. Then suddenly we thought, the Alan, he was telling me, I don't know, he had no like a theory behind. He said, okay, why don't we reduce the height? So then he just said that. So we thought, okay, just reducing height. Then we realized increasing pressure, decrease the bubbles.
Yeah,
so
definitely.
Yeah. So then we thought, okay, there is some theory behind that. But it's, yeah, that is actually, that's a good point. Actually, sometimes we don't really care about that, the thing in the smaller way. I thought, okay, so just micrometer height, what is going to change? But the micrometer changes is changed a lot. And the second one, I thought, oh, I have a question.
Next slide.
No, next one. Maybe not this one. Yeah, this one. What is that one? Then the F5 cable, the one, the fourth one is the same, right?
Which one are we talking about? Part B or part C?
Part B.
Part B, and then the fourth box. Yeah, I did kind of skip over that. So where are we here?
So that outlet.
Yeah, it's
the position of that.
so it's a dead space. The capillary is like a tube. I think that one is an outlet.
Right, so this here and there is a
Yeah.
because that makes sense.
So so yeah, all they did was move the outlet closer to that right angle just to prevent that dead space. A lot of this paper talks about ways to get rid of dead spaces, and sometimes you can just design it out like they show there in the fourth one over of part B. But that's not always possible. Sometimes you have restrictions. So they talk about other options like filling with PDMS or whatnot. But what really what really resonated with me was that bubbles are not inherently caused by gases or pressure or temperature. You have to have geometries in your device that will cause the bubble. And so like micro cavitations and stuff,
Yeah.
like
So that is
Harvey nuclei.
absolutely. We think sometimes there is a lot of air in the liquid, but even there is a lot of air in the liquids, we have the possible option to rid of that bubbles without vacuuming or doing something. I like the first one, the first one, the angle.
Mm.
I was trying to do that one in our device
Mhm.
because we keep getting that our channel is very straight. We cannot avoid like 100% bubble free area. But I saw a paper, you are making the angle 45 degrees. So then we can reduce that, completely rid of the bubble.
Yeah.
So, but we cannot, we have the restriction, limitation to machining here. That's what we did. But I like the idea, that is actually really good. Somewhere, if you are doing some devices in future, we have to really think about that.
About angles and design. I totally agree. And then there is definitely a lot of other theory behind pressure and how pressure works in your device. And maybe we can do a part 2 journal club.
What is the real principles behind there in the angle, how the angle is preventing the air?
Yeah, so they do go into the actual physics of it. For the sake of time, what do we have? Oh, we still have 9 minutes to discuss. Yeah. So they call it the advancing angle and the receding angle. So if we look at part A of this figure, the advancing angle of the liquid needs to be less than the receding angle inside of the crevice. So and this can they talk about wettability of your surface as well. Surface chemistry is also very important. If it's hydrophobic, you're more likely to have larger wetting angles that will cause bubbles, whereas if it's hydrophilic, the liquid really wants to grab onto the surface and you'll have smaller advancing angles. But typically in fluidic devices, we usually are working with a moderately hydrophobic surface. Like especially here in our lab, we work with polycarbonate. So we could do surface treatments, but usually that's not the case.
Yeah.
But it is about advancing angles and the hydrophobicity of your surface, and then also the angles of your crevice. Especially with these micro crevices though, like if you look at part B, that's a picture of PDMS at a very close angle. It's really hard to get rid of those crevices. Even if for us, when we're working in polycarbonate, we polish the surfaces. If you were to look at it, it's not perfectly smooth. No. If you do like high resolution imaging, and they show that in part C here, that's a highly polished silicon wafer, you still get cavitations. It's
I understand the surface treatment and angles is really helpful to minimize the bubbles. But have you ever think about the flow rate?
well, so yes, flow rate is directly correlated with pressure. Pressure equals velocity times hold on. Pressure equals velocity times it's like volume or something. So flow rate is velocity, and pressure here is directly correlated through Henry's law of growing bubbles. So with that equation, pressure equals velocity times area. Yes, we can have more theory in our designs. We need to think more about the dimensions of our device and the flow rates that we're using. We'll get there. I think between me and you, or I'll be your assistant.
If I'm working completely in the microfluidic device, of course I can, put a lot, but now my microfluidic part is super tight, small area. It's like other part is, expanding, that is very small, but I feel like that, yeah, based on my experience, I think flow rate is one of the important part also, because yes, all of them is equally contributing in this one, surface treatment and angle pressure.
Well, I'll say it right now, next Friday, I'll do a part 2 of microfluidics and we'll look at pressure.
Sure, yeah.
Because yeah, I've definitely been reading in it, and if you don't consistently work with it, it does kind of evaporate. I'm having a hard time with microfluidics as well. None of it's really complicated. There's just a lot of details. So to keep it all in working memory, that's kind of difficult. So next week, yeah, let's go ahead and do a focus on that. What questions do you have? So I'm gonna put these questions in the comment section of YouTube, and then I'm gonna go back and answer the questions, but and don't feel bad about whether your question is in depth or not. So Ash, what question would you like answered based on what you've seen today?
So I'm not very familiar with microfluidics, but I think I really like to see the solutions to, get rid of bubbles. How we do it, what is the mechanism, and what is the physics behind that? How we can remove it, and what kind of experiments have been done to make sure that, okay, we can get rid of these bubbles?
Well, this paper did go through that. I just didn't go into detail based on our time constraints, but really quickly, it's design. So eliminating dead spaces. Remember those corners where the liquid just goes over it? Eliminating dead spaces. And then they also recommend pre-wetting your device with something besides water. From chemistry, water is very polar through hydrogen bonds. The oxygen is very strongly electronegative, which pulls away charge from the hydrogen bonds. So the hydrogens become positive and pull in the oxygen from the other water, and then it's like a really tight kind of surface tension, which increases the development of air pockets that won't go away. So they show that one figure where they recommend maybe instead of water, use something that has less surface tension, such as ethanol or water with SDS. So that's one recommendation. So design, and then also wettability. They start the paper off though saying that most people, which I think we're guilty of this too, is having leaky connections that are not totally tight. I've definitely seen that in my experience because I use lure lock systems. And if you don't really get those tight, you're going to have air leaking into your device. So and they recommend getting around that by using resin instead of lure locks, like fill it in with epoxy or PDMS or something else. So we're getting there. We're getting there. But Jasmine, if you had one or two questions.
Okay, that's all the questions. What do you have present today?
Yeah. Okay. If I were to have one question answered, I want to know if we can modulate pressure in a microfluidic device by other means besides velocity of our liquid or the dimension of the device. Like, can we put a microfluidic device inside of a pressure chamber and make the environment pressurized?
We can do that, but do you think the turbulence will cause anything?
The turbulence of the flow, of the liquid flow?
Because you said you were being inside the pressure chamber?
Yeah, just put the whole thing inside of a pressure chamber and make everything the same pressure so that there are no pressure drops. regardless of dimensions of your device and
Maybe possible.
it's possible.
Yeah.
Okay. So, and I know that's not always an option, especially like,
Slowness cause errors.
mhm.
That is what we have to, the flow should be smooth and flow optimization should be. And also when we are putting inside the pressure chamber, I'm like thinking how the flow is that uniform or it's like, I don't know what kind of pressure chamber you are talking about, I have no idea.
Just like a big vacuum chamber or like a positive pressure chamber, something big where you can just put your whole system in there. And then also it's interesting, how does turbulence cause bubbles? That would be an interesting
Yeah,
question.
correct, yeah, maybe. Yeah.
So I'll try and go into that in part 2 next week. I already kind of have a working idea, but okay, with that, that is our 15 minutes of discussion. Thank you so much, Jasmine, for coming. That was fun. Ash, thank you for coming.
Thank you.
And then to the rest of my peers here in lab, feel free to present a paper anytime you want. We should let everybody know what the paper is at least a day in advance though. So with that, have a great weekend and we'll see you next week. Bye.
Yeah, I'll see you guys later.
Bye. Oh.